Hello everyone. So today we're going to continue with our venture into magnet. Now, but today we'll actually look at the name of this topic a little bit more closely. It's called electromagnet. So that means there are electricity involved in these kind of magnetism effects. So how does the electricity come in? Well, it turns out that after careful studying, scientists discovered that any current carrying wire, not just like a regular wire, it has to have electron running in it, is surrounded by a magnetic field. So when you have moving electron running inside a wire, there will be magnetic field around that wire generated by that moving current. Now, it turns out that it doesn't even lead the wire. Just a moving electron flying in free space generate magnetic field. Well, not just electron. You can also have flying photons in space, and it will also generate magnetic field. As long as it's a charged object and is moving, it will generate a magnetic field. Now, we need to find out how to deal with the magnetic field generated by such things like current carrying wire. So we have a right hand rule for that. So we have to use our hand. Now, this is called the first right hand rule. There are three in total. Today we'll only look at two of them. So this first right hand rule is for finding out the magnetic field around a wire that carries current. Now, so to understand this right hand rule, we'll first write down the definition. So what you have to do in this right hand rule is have your thumb pointing, so like like when you give a like button, so like this. So let me show you in this picture right here, which I spent a long time to draw. Okay, so now look at this picture. Before anyone asks the question, yes, it only has three fingers. I forgot to draw the pinkies, okay? So, no problem. Mickey Mouse hand. So look at this hand right here. So now, the thing that you're holding is a wire, okay? The thing that you're holding onto is a wire. So the wire has current, and the current is going, down diagonally to a lower right-hand corner at this instant. And as the current flows through this wire, it will generate a magnetic field. So the magnetic field will be going around the wire like a circular loop. Now, so what we need to do is to use our hand to predict which direction will this magnetic field actually turn. Does it turn clockwise or counterclockwise? So the way to do it is line up your thumb, right? Line up your thumb with the direction of the current, and then you let your finger tells you which direction is the magnetic field. Now, if you want to, freeze this page, stop this video at the moment and you'll copy that picture down, be my guest. Now, otherwise, I will show you this part right here. So this is a computer generated picture, which is even better. So as you can see, the thumb lines up with the current, and the rest of your finger tells you which way the magnetic field will circle around. So look at picture B. So that's the magnetic field going around a current carrying wire. Our thumbs are just telling us which way does it go. Does it go clockwise or does it go counterclockwise? Now, let's go back to, now we'll do more exercise. And don't worry, let's write that down first. So your thumb is the current. Okay, point your thumb to the direction of the current. Okay, so I, your current, which is measured in M, right? Now, the rest of your finger will be the direction of the magnetic field. So it will be the direction of the magnetic field. Now, I haven't told you the unit for magnetic field yet, or the symbol. The symbol, okay, so the symbol for magnetic field is B. Okay, so we cannot use M because it will be magnetic field M, mass is also M, then we get really confused. Electric field, we could use E because it was available, but for magnetic field, unfortunately, magnetic field, the symbol is B. So sometimes we even call it B field. So now, in this picture right here, the color picture on my screen, back and right on yours, your thumb goes in the direction of the current, whereas the rest of your finger is the direction of the magnetic field, which is the B field, right? Okay, so let's move to this next page. Now let me erase some of these first so that we can have a fresh start. Okay, so now one of the problems that we have right now is how do we represent 3D information on a 2D piece of paper? So now you have your regular up and down. So this direction is up toward the top of the ceiling, right? And down, which is toward the floor. No one disagree with that, I hope. But then we also have these two directions. Well, that's usually called left and right. I think I can get a agreement with almost everyone with those two directions too. But now here's the problem. You do realize in a 3D space there's two more directions, right? Up is where the ceiling is, down is where the floor is, right hand side is where the wall is, and the left hand side is where the door is. But what about the direction that's pointing toward yourself right now, out of the screen? What about that direction? And what about the direction that goes into the screen, into the projection screen that you're looking at right now? So there's into the screen and out of the screen, those two directions, right? You need 6 directions to actually represent a 3D space. Well, the problem is going to be solved by 2 more symbols. So if we want to represent into the page, we'll draw a little cross. So little cross means into the page. So we'll draw a cross like that, and that represents into the page. So this little cross is into the page. So into the page. If I want to represent out of the page, which is toward you right now, then I will use the little dot, and that represent out of the page. So a little dot represent out of the page. So little dot is out of the page. So out of page. So now we can have 6 directions, right? We can have into the page and out of the page also. Okay, so one way to think about it is this looks like an arrow. An arrow is sharp on one side. At the front, at the beginning, is sharp, right? And on the back of an arrow, you always see that cross. So that's one way to think about it. Now, okay, so let's look at a few examples, right? Now, so we look at a few examples, and to look at this, I'll actually, okay, I am probably going to regret this, but let me try and see if it works. Over here, there. Okay. So that means I'm not going to be directly in front of the microphone, so you might have to adjust the volume if you can't hear me. I'll try to, yell. All right. Okay, hopefully you can still hear me, because I am adjusting the microphone right now. Hopefully it doesn't fall down or anything. So now, going back to the last point, which was the into the page and out the page, it's really easy. The way I look at it is, look at the thumb, right? So if I bring the thumb into, let me get the microphone to high somewhere here. Okay, look at the thumb. If you look at the thumb, you see a little dot, right? When I'm pointing toward you, you see a little dot. You see my thumb. So that's called out of the page. So imagine that this is the page. That's called out of the page because all you can see is my thumb. Now, if I point toward the page, this is called into the page because if you actually look at the back of your hand, you see that star right there? That's the cross. So that's into the page, out of the page, into the page, out of the page. Now, you have to assume that this is your Nook page right now, right? So that's one page of your Nook right now. So you see those 4 examples. Now, so what is in front of the wire? So that thing is just a wire. Just like a regular wire with current going one way or another, right? Or you can have my PMIC wire. This is a piece of paper. So current can either go down or current can go up. Now, magnetic field makes magnet move. Magnetic field makes magnet move. So I have, so for example, what happened in that picture is what happened if you put a little compass in front of a wire and you let current go through the wire. So basically, that's the phenomenon. Okay, so you have a compass needle in front of a wire and you let current go through it. That will be the first question, that one right here, and this one right here. In the second question and the third one is what if the compass needle is behind the wire and you let current go through that wire? So now it's behind, right? Okay. So now, so let me demonstrate how to use the first right-hand rule. So this is the first right-hand rule. So here's a wire, and the compass needle is in front. So I need to look at the direction of the current first. So for the first one, current is going in the direction from the top to bottom. So in this first question, current is going from, this is positive, that's negative, right? So current is going this way. So in the second question, it's going this way. So we can reverse it later, right? So first question, the current is going down, and in the second question, current is going up. So now we look at the two compasses. So if the current is going up or going down in the first example, and your compass is in front of it, now what happened is I'll try to do it really close. Okay, so you line up your thumb with the direction of the current, which is going up, and look at your finger. And you move around like this. Now look at your finger in front of the wire. When your finger are behind the wire, you're going to the left. But once you wrap around and go in front of the wire, you're actually going to the right. So that's the direction of the magnetic field in front of the wire if the current is going up. Okay, so if the current is going up, you have the direction of the magnetic field in front of the wire going to the right. So that is this question. Okay, so if the current is going up that way, so maybe I should use my paper one, right? I don't know if you can actually see the current. So if the current is going up, you wrap your fingers around it, your thumb line up with the current, and the rest of your finger goes around. As you move in front of the wire, your finger is moving to the right. So therefore, this is the direction of the magnetic field of a compass needle in front of a wire. So this one is just reverse. So now here's the reverse, right? So you see now the current is going down, so that's for like this case right here. And so if you, well, then you have to grab your finger this way. So you have to have your thumb pointing down then, right? So look, as your finger moves in front of the wire, it's moving to the left. When you move behind it, I know it's really hard to see, but when you're behind it, it actually moves to the right. But when you're in front, it goes this way. So therefore, points to the left. So that's the first right-hand rule. Now, it's essentially the same idea with the next two examples. So I hope you can figure that out. I'll go over those two with you when I come back personally. So I want you to go through that. Now for the next two on your note, so for the next two on your note, you can basically look at it as something like this. So now let's do the next two. So you have a, okay, so now what this picture represents, there's a little cross in here. What it means is current is currently going, now can you see that little dot? Yeah, you can. So that means current is going into or out of the page. Think about it again, using your thumb. So this is, when you see the X, right? That means into the page. So this current is going into the page. So now, when your thumb should point into the page and turn it around like this. So that means the current should be going this way. Okay, so your current, so the current is going into the page, so the magnetic field around this should be going in this direction, which is usually what we call clockwise. So look at my thumb going into the page, that's the current, and look at my magnetic field going around the wire. So this is a situation where the wire is directly pointing toward you, like this. So you're looking at the wire from the tip of it, and current is going into the page, So you have magnetic field that goes around the wire like this, right? Before we were looking at it this way, now we're looking at it this way. So that's why it goes around. So if your thumb is in the same direction as the current, then your finger wraps around with the magnetic field. So this is the direction of the magnetic field of that wire. Now, exactly the same idea, but reverse, will give you the answer to the second question. Again, I'll go through that with you when I come back. Now let's go back to the note. Okay, so let's go back to the note. And so back to the note. Now we have one of these filled in already. So I will just quickly fill this in. So if current goes this way, or if current goes that way, then the needle should be pointing to the left on the first one. So if you need to copy those two, you can do so right now too. All right. So now we also did the third one. So this one goes this way. So it goes around in a circle. So if you have like a compass needle, if you have 4 compass needles, then they should be going around. Okay. So imagine that these are compasses. These are compasses. And this little thing is a wire carrying current into the page. Okay, so wire carrying current into the page. All right. Okay. Now, so one more thing. Okay, so before we introduce, note that the current compass, right? Notice compass always point in the direction as the magnetic field. Okay. So now, so we have seen that movement of electrons can create a magnetic field. But how does this apply to permanent magnet, like, for example, a bar magnet? Well, certain metals, for example, like iron, cobalt, or nickel, or even like neodymium, which is a really, really strong magnetic metal, they have domains. Okay, so they have domains. Now, in a piece of this metal, the spinning of these electrons lies in area called domains. In an unmagnetized piece of metal, the domains are lined up randomly. So you might have, a little north-south this way, but you might have, so what this means is, for example, like north and south. So you might have a domain this way, and you might have another little north-south like this way, and one this way. So a random piece of metal have its magnetic domain pointing in some random directions. So therefore, overall, it all cancels out. So overall, this piece of magnet has no magnetic direction that are dominant. So it doesn't behave like a regular magnet. On the other hand, we could, however, charge up a piece of magnet or charge up a piece of metal so that we force the electron to all align and spin in the same direction. Now, so when we do that, or another thing we can do is we put this piece of metal right here, which is unmagnetized, and put it next to something that is strongly magnetized. For example, we mine some neodymium alloy. Neodymium is naturally magnetized and is one of the strongest magnetic element you can find on Earth. So let's say you put this giant metal bar next to a giant neodymium ore for like 10 days. Now slowly, this giant neodymium ore has this magnetic field lined up perfectly. Okay, or really strongly at least. Really, really strongly, just like a bar magnet. Now what happened is those electrons that are spinning in different direction would eventually want to line up with the magnetic field. that is near them. So what will happen is after a while, these little electrons will start to, well, fall into place. Now they might not like all agree or 100% agree to each other. Maybe you have, the occasional, occasional electron that say, no, I'm too cool to follow the general trend. I'm going to create my own trend. You might have that, but give it like most of them follows. And what happened is, well, when most of them follows, then there's a general magnetic field that you can predict. So it will be, like a north and a south pole like this. So this is a bar magnet, or the creation of those metal bar magnets. Now, unfortunately, these domains are not permanent. I mean, technically speaking, if it's that easy to actually charge it up, it must be really easy to screw it up too, right? And have the electron spinning in different direction. That's actually true. So that's why if you have a bar magnet and you drop it on the ground for like 10 or 20 times, it will lose its magnetic effect. And you will have to put it next to the neodymium for a few days and charge it back up again, right? So it will work. Now, of course, today, so I will show you when I come back, there is actually a machine, a small machine that we have, that will pass a strong current through the metal and force all the electrons to line up more or less and make the magnetic effect stronger instantaneously instead of waiting for like a few days. Okay, so that is the idea. Now, okay, so the last bit of today's lesson will be involving solenoid. Solenoid is a cool name, but what it really is just, well, a coil of wire. It's a coil of wire. Okay, so it's basically just a coil of wire. Now, a solenoid is also called an electromagnet. And it's going to be our main focus for this year, for the rest of the year. It's called an electromagnet. So a solenoid, when you hook up a solenoid into a power source and you let current run through the solenoid, you actually get magnetism from it. Now, so since I'm not here today, I don't want to introduce the solenoid right-hand rule, because the first right-hand rule and the solenoid right-hand rule, which I call the second one, are very similar. So that means, for now, just take my word for it, that if you have, so I think I have a picture of that. So there we go, a solenoid. And then if you hook up the solenoid into a power source, it will behave like a magnet. If you cut the power source, the magnetic field will die. So that means this is a kind of magnet that we can turn on and shut off at our view. Okay, so if we want to turn it on, give it energy, give it current. If you want to shut it off, cut the battery, cut the current, and the magnet will actually die down. So it's a very useful magnet where you can actually control if it's on or off. Pretty cool, eh? So we will introduce a direction next class. Okay, so we just do the equation for today. So now, what we find in this equation is the magnetic field inside the solenoid. Inside the solenoid. So there are magnetic field inside the solenoid, inside the circle of the coils of wires. So inside those coils of wire, we want to find out how strong is the magnetic field inside, based on a few things. Based on the length of the solenoid, which is in this picture L, and it also based on the number of loops in your solenoid. So one circle is one loop. So like, for example, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 loops of wire. So we say big N equal to 9. 9 loops of wire, and we have the length, right? The length is L. Okay, now let me show you the equation. And we will do the direction. I'll teach you how to do the direction when I come back. Okay? All right. So we want to calculate the magnetic field inside solenoid. And we can use this equation. Now I have to define like some of the terms. So the magnetic field inside a solenoid is equal to mu naught times n times I. So mu naught n I. Okay, so B is magnetic field. So let's write it down on the left. So B is magnetic field. So the strength of the magnetic field, which is measured in Tesla. Okay, so it's measured in Tesla. And most of the time we'll just use T. Okay, now if you don't know, Tesla is this guy. It's named after him, Nikola Tesla, one of the greatest inventor and scientist of, well, I guess the last century, right? Nikola Tesla. Now, so magnetic field is measured in Tesla. Let me give you something in perspective, though. So the magnetic field that we measured is usually quite small. Okay, so for example, Earth. Remember last time I showed you a video, and in the video it shows you Earth's magnetic field blocking the solar radiation from hitting us and the solar storm from hitting us. Well, Earth's magnetic field, so Earth's magnetic field is only 0.000032 Tesla. It's really, really small. Earth has a magnetic field, yes, but it's actually quite small. Now, the strongest magnet that we have ever created, not created, I guess mined, the strongest permanent magnet ever mined on Earth, that means neodymium, that kind of element, is about 5 Tesla. The strongest man-made magnet we have ever created with solenoid, so we can use solenoid to create magnets, remember. So the strongest magnetic field we have ever created on Earth is about 100 Tesla. So Tesla as a unit for magnetic field, if in your calculation you get like a couple thousand Tesla, something is wrong. Okay? Now, alright. Now the next unit is this mu naught. So it is a mu with a little circle. So it's called mu naught. And that is called the permeability of free space, and it is on the formula sheet. So of space. That number is on the formula sheet. If you could, so it's 4 pi times 10 to the negative 7. Okay, so 4 pi times 10 to the negative 7. Okay, current. Well, I is current, which is measured in ampere. I don't think we need to concern about that too much. Now, what about this little n? This little n is how many loops of wire. Now, remember in the picture that we looked at before, we have 9 loops of wire. So how many loops of wire do you have per meter? So it's loops per meter. So for example, if you get a solenoid like that, so let's say the length of the solenoid is about, well, let's say it's 0.2 meter, and you have 25 loops. Okay, so then little n in this example would equal to 25 loops divided by 0.2, which is going to be 125 loops per meter. Right? So the little n is just how many loops of wire do you have divided by the length of the solenoid that you created. Okay, so all good. Now, one thing that I will concern a little bit about this kind of calculation is the permeability of free space constant. You see, you cannot actually do 4 pi times 10 to the power of 7, negative 7 in this case, directly on your calculator. It's kind of weird. So usually what you have to type is something like this. So what I would usually do is something like this. I would type pi, multiply by, and then I would do the 4e7. Remember the exponents button, the exp button? Yeah, the one that I asked you to use instead of the times 10 to the power of. It's either e or e to the power of something. So, or in some calculator, it's the times 10 to the power of button. So I would do 4 multiply by e, so 4 e negative 7. So I would do it this way and multiply the pi toward it at the end or at the beginning. So when you want to deal with that constant, you kind of need to do it this way. Okay. So now we'll just do one example and then we'll so let's see. So in this example, so what we have is a solenoid is 25 centimeters long and has a 1,000 loop. If the solenoid has a diameter of 4 centimeters and a current of 9 amp, what is the magnetic field inside the solenoid? Okay, so we want the solenoid, and it's equal to little n I. Okay, now here we go. So mu naught is the permeability of free space, which is 4 pi times 10 to the negative 7. I know when I put it in, I have to be careful about this number. Multiply by loop per meter. I have 1,000 loops, so put 1,000 first. Centimeters have to change to meters, so 0.25 in meter. And then multiply by, so I have like most of this stuff already. Now I need the current, which is 9 amp. Now you might say, Mr. Chang, there's a number that we didn't even touch at all. Oh yeah, the magnetic field inside a solenoid is supposed to be a constant, regardless of where you put your detector. So as long as you are within the center of that wire loop, doesn't matter where you measure it, it should be the same amount of magnetic field. So I don't need to know your diameter. Okay, unless it's like kilometers long, then it might get weaker as you go toward the side instead of right in the middle. Now, so if I get all of that, substitute into the equation, then what you should get is about 0.0452 Tesla. So that's how strong this electromagnet is. When you look at the Earth number, it's stronger than the Earth already. Weaker than maybe like a neodymium magnet by a lot, but quite a lot stronger than Earth's magnetic field. All right. So now there's a worksheet number 1 associated with this day 1 note. Of course, we haven't covered right-hand rule number 2. So any question that asks you for the direction, for example, so any question that asks for the direction of the magnetic field outside the north, we won't be able to do. But the actual calculation you could, right? The actual calculations of the magnetic field inside the north you can do, and current around a wire you can also do. It's just the current, the direction of the magnetic field inside a solenoid. Those kind you don't do yet. Okay, so next class we will go over them. All right, so now that should be it for everything that we have. Oh yeah, that should be it. Okay, so I'll come back, and if you have any questions, then of course feel free to email me. I will try to check my email and respond to it. Okay, thank you. Bye.